And oh yes, my last year, and they got something to work right, so now I'm doing PowerPoint. Believe it or not, I didn't do PowerPoint. I like Keynote, and then I had to move everything to the smart board. And y'all, I started with colored chalk and a chalkboard. Like truly. All right, so here's this, which was already up there. Okay, so lab does start this week, so make sure you attend the section you registered for, Monday, Tuesday, or Wednesday, 1 o'clock. I believe you're meeting in here at the beginning. And he's going to talk about safety and stuff. Okay, we got some different safeties. Okay, in case you're worried about, that old video where the gal cut her hand with a glass rod and all the blood went everywhere. That one's gone. I had somebody pass out. It's highly fake. I mean, it's obviously fake, right? To be fair to the poor student, something else was going on too. Okay, so my students tell me that coming to class every day really helps. Be on time. Study regularly. That means that you go home today and you start reading chapter 1. You get on your sampling. Get with it. Don't wait a week. You're already a week behind. Okay? Really start today. So if your other classes say, well, we won't really start till Wednesday, you got my class today. Okay? All right. Do your problem assignments online and in the textbook. I tend to make the online homework due a couple days before the test to try to force you to do it before the test so that you aren't doing it the night before the test. Okay? You can go back over it and all that, but I wanted you to get it done. Okay, make use of the text website and any extra study aids like the model kit and stuff, and come to office hours and do not get behind. You'll be like, I'm cool, I got this. Today, you're going to go, I got this, okay? And then by next week, you'll be, oh, okay? So it's going to come. So just hang with it. It is right now, you need to think of it as 4 months of your life. Okay? 4 months, I'll be done with organic 1. Okay? Another 4 months, I'll be done with organic 2. Okay? You can do this. You can do this. I've had people come in here, I can't do this class, it's so hard. Okay? It's not. You have to take it a piece at a time and just stay with it. Okay? But don't go hunting for a week and then come back and be mad at me because I covered almost an entire chapter and you missed it all. Okay? Don't be doing that. Just put off that hunting until Thanksgiving week. Okay? You get a whole week for Thanksgiving this year. I think we might all cry in October, though, when we don't have our fall break.
That's nuts.
Are you ready to do that? We'll do that together. Okay? So, what I want you to understand, too, is that there are billions of organic molecules. Billions! Okay? There are more organic molecules than inorganic molecules added together. Okay? Factor of 10 to the third or something. There's just huge numbers. And you can't memorize everything. You can't look at every molecule I put up here and go, oh, that's a new molecule. What is it? Okay. All right. Calm down. Deep breaths. All right. And what you need to do is look at what you know about that molecule. You know what it is. You know what kind of functional group it is. And then that tells you something about what it does. Its reactivity. Okay. So you're going to be looking for those. Look for patterns. Okay. You're going to be a doctor every time a patient comes into your office and you have to listen to their heart and look in their ears and their blood pressure and all that stuff. You can't panic every time, right? No, because you know the pattern. You know what it should be. You know that if this is off, look for this, okay? Same kind of thinking, all right? So you're going to have to be able to apply what you learn in here to new things. And on the test, you may see something new that you have to take what you learn and figure it out. You will be able to do that. problems, and come to work. Come to work. Come to class to work. I don't know. Whatever. Okay. This is by Friedrich Wöhler, and he wrote this in 1835. So what year is it now? 2018. Okay, so there's been a few more years of organic chemistry since then. Okay, and he said, organic chemistry nowadays almost drives me mad. To me, it appears like a primeval tropical forest full of the most remarkable things. A dreadful, endless jungle into which one does not dare go, for there seems to be no way out. You do not want to get lost in the jungle. Okay, so start at the beginning, and we're going to work our way through. Okay, and you can do this on this. Okay, we're going to talk about old Friedrich again. Okay, chapter 1 is introduction and review. And I want you to know that the review parts, I'm not going to spend a lot of time on them. Okay? Like, I'm not going to go through the whole electron configuration again. I'm not going to go through the whole, this is a proton, this is a neutron thing. Okay? We're moving on. Surely we got that by now. Okay? So, if you are very confused by that for whatever reason, maybe you took neurochemistry 20 years ago, then you need to pay more attention to that in that chapter and come see me and I'll go over it with you. Okay? Okay, so this guy right here, is he coming? I don't know. Can you see any writing? Here we go. Okay. This guy right here is John Jacob Berzelius, and he was the one who coined the phrase organic chemistry in 1807. We got to throw a little history in there so you know where we're coming from. Okay, and the original definition of organic chemistry was not pain and suffering, even though that might be yours right now. Okay, it was the study of compounds from living sources. Living sources. So, name a living source. A plant, right? Okay, a plant, an animal. Those are living sources, not rocks. Rocks are not living, at least in this universe. Okay. At least in, maybe I shouldn't have said that, on this planet, I should say. We don't know about the whole universe, right? Okay. So he's the guy who started it all. This is Wohler, the guy who said the other deal about the jungle. All right, there he is. Don't you love these cute pictures? Okay, he performed an experiment in 1823 that changed our view of organic chemistry forever. Okay, so this is his experiment. He took ammonium cyanate, okay, which is from non-living sources. And he did some stuff too. We're not going to worry about exactly what he did. But what he made is what's exciting. He made this compound, okay? Do you know, anybody know what that is? It's urea. I don't know if this is where the term eureka came from or not. I thought it was kind of a good idea, though. Okay, there's urea. Urea is from living compounds, living sources. This was the first time that somebody took something inorganic and converted it to something that was organic. It was amazing, okay? Back in the early 1800s, they believed in this thing called the vital force, that there was this extra special force in living things that allowed them to grow and reproduce and think. Well, the plants don't think, I guess. But, you know, that kind of stuff. So, Wohler's doing this just like blew everybody's mind. And he wrote to Berzelius a little letter, and in the letter he says, I must tell you that I can make urea without the use of kidneys, either man or dog. Ammonium cyanate is urea. And that just changed everybody's view because they figured out that they could make compounds from things that weren't from living sources. Like it didn't have that special vital force in there when they started. Okay? Not sure what's going on with there. So the current definition of organic chemistry now is the study of compounds based on the element carbon. Now, anybody going, wait a minute, ammonium cyanide had carbon in it. Anybody think that? Gosh, are y'all awake? Okay, well that has ionic bonds and it's pretty much an inorganic thing. So like sodium carbonate. We know what that is, right? Sodium carbonate? Okay. That is, carbonate is not considered to be organic. It's inorganic. Okay, so there are a few things like that that are those ions. Bicarbonate, that's another one that's considered to be inorganic. Okay, so just because it's that carbon in it doesn't make it organic. But if you have more than one, then it pretty much is. Can I do that? Will it go? Ooh. Okay, so good old carbon is C. That is our favorite element. Okay, it is it's element number 6, and its weight up on the table is 12.011. Okay. Okay. It has 3 main allotropes. What's an allotrope? Ooh, do you remember that term? Okay, that's all right. It's not an isotope, it's an allotrope. Allotropes are just different forms of an element. Okay, so another example is oxygen. Oxygen has 2 allotropes, O2, oxygen, and ozone, O3. Okay, those are called allotropes. Okay, so our allotropes are graphite, diamond, and this weird looking thing. Looks kind of like a soccer ball. It's called Buckminster fullerene. Has anyone ever heard of Buckminster Fuller? Boy, you are learning so much today, I tell you. Okay, he was an architect. Okay, and he did the geodesic dome. Have you seen like dome houses and things? If you drive down to Austin, there are several domey things on the way. We just did that. He was the architect, and these are very similar to what he did, and that's how come they named them that. These are fairly recent, like 20 years recent, okay? It's not like something that's been around for a long time. They found them in soot, and they're found when lightning strikes, stuff like that. It's kind of different, yeah. And we'll talk a little bit more about them later on. Graphite and diamond, unfortunately, we're not going to talk about very much. The difference, do you know the difference between graphite and diamond? Besides the diamonds look so much nicer. Okay. Well, graphite, you have sheets of carbons connected to each other. Okay. So when you write on a piece of paper, you're not really using a lead pencil. You're using a graphite pencil, right? You are sloughing off the layers of graphite onto the paper, okay? Diamond, nothing sloughs off. There are actually bonds formed between the layers. So you could take graphite, and they do this. They make them in the lab now. They take graphite and put it under high pressure and convert it to diamond, okay? And when you go out to buy jewelry, you may run into some of those diamonds. And you can even get different colored ones. The things that make the colors are imperfections, okay, actually, that make the colors. And just like a diamond that's mined, the ones that are formed in the lab don't come out looking like gems. They have to be cut properly, okay, in order to get them to look so nice. Has anybody ever been to the Smithsonian and seen the Hope Diamond? It's blue. It's pretty cool. If you get a chance to go. I'm going to tell you to go. And it's about like this big around. It's huge. Okay, and they have it. Like, I was kind of disappointed. I thought there'd be a little case to be the diamond right there. Oh, no. It's like behind this, behind this, behind this. It's like way back there for all the security and everything, I guess. It's way back there. So. But it still was cool to see. Okay. Let's see what I got next. Okay, so carbon, I still have 10 minutes. We're doing good. Okay. Carbon has 6 electrons. This is its electron configuration. 1s2, 2s2, 2p2. Does that ring a bell? Okay. One thing I do want to make sure you know, I don't seem to have a ruler. I'll get a yardstick for next class. Okay. You need to remember that the first 2 columns fill the s orbitals, and these 6 fill the p's, except for helium. Okay? The middle fill what orbitals? The d's. Okay, but they're all inorganic, so make that worry about them. Okay? We're going to basically talk about the guys over here. Okay? Okay, so when you fill the orbitals, remember that you fill in order of the level, and one electron is spinning one way, and one is, am I doing it right? One is spinning the other way, so that they will go together. They only go together in the same orbital because they have opposite spin. That makes their magnetic fields go the opposite way, so that's how they'll go together. Otherwise, they don't want to be by each other. Okay, so this is one electron up, one electron down. And if you were to draw this out, it wouldn't matter if you did up or down first, just so long as you did one of each. Okay, and then you go to the S, and we fill 2s. We're on the second level. And then when we get to the p's, you notice they aren't buddied up. You put one in each, and then you double up, right? That all kind of, okay, because this is all going to come back to haunt you. Okay. Okay. All right, and you see down here I wrote 2px, 2py. What's the third one? Z, 2pz. Okay, I got a picture of the orbitals. Okay. Okay, how many valence electrons does carbon have? Look up there and tell me.
6.
No, it has 6 total. What's valence? Nope. It's 4, the only other option, right? Okay, so valence electrons is the number of electrons in the outermost shell. So these 2 count even though they have a buddy. Okay, what's our magic number for compounds making bonds? What's the number that they always want to get to?
8.
8. Okay, that 8 is still real important. We call that the octet. Let's see. Okay, so for carbon to get a complete octet, it needs 4 electrons. We're going to talk about how it gets those. Remember I told you there were billions of organic molecules and hardly any inorganic, okay? I mean, they only have 1 class for inorganic. You can do bunches of classes in organic if you wanted to. If I could get you to take them. Okay, so 4 electrons for a complete octet, and carbon will combine with itself in numerous ways over and over and over. And because of that, that's what makes it so cool. Okay, that's how come we're carbon-based life forms and not silicon-based life forms. Although that was in an episode of Star Trek, wasn't it? The original show. Way back there was a silicon-based life form. Somehow we were both on the planet breathing the air at the same time, but you know. Yeah, they like to break those rules. Kind of like the talking rule. We can always communicate. Okay, so in order for carbon to get that octet, it will make 4 covalent bonds. Okay, so what's a covalent bond?
Sharing electrons.
Sharing, okay? What's the other kind of bond?
Ionic.
Ionic, okay? And then there's that weird one. Yeah. Okay, so here is my picture of this. This is an s orbital. S for sphere, okay? It looks like a sphere, okay? Remember what an orbital actually is. It's simply a probability of where an electron is located in space. That's it, okay? It doesn't mean the electron's going like that. They don't know how the electron's going, okay? But it is being held in that area by the nucleus. The nucleus has what charge? The nucleus has what charge? Positive. Electrons are? What are neutrons? Neutral. Just make sure you got it. All right, so here is our s orbital. This picture is on your slides, so don't feel like you have to try to draw it. The electron density is highest at the nucleus. It's closer to the nucleus, and then it starts to drop off. Okay, and that's how, it's kind of like thinking about the planet Earth, and we have this envelope of atmosphere, and as you go farther and farther out, it starts to drop off. Okay, it's the same kind of thing. All right, so that is basically an s orbital. So what's the difference between the 1s and the 2s, you think? The 1s is littler and the 2s is bigger. Okay, and what's really weird is to think about them all on top of each other. I go to a big element. Wait, there we go. All right, so here are the 2p orbitals. Remember, there was 2px, 2py, and 2pz. Okay. There are 3 2p orbitals oriented at right angles to each other. Each p orbital consists of 2 lobes. So you have a bottom and you have a top. It's like a balloon that's tied in the middle. Okay? And you're going in the 3 directions, x, y, and z. Okay? And that's what this is. There's the blue, the green, and the purple. Okay? They look like balloons. You will see pictures like this in your textbook. I don't know if this one is actually from that book or not. I've had so many over the years. All right, so those are the 3 put on top of each other. Now, don't remember what an orbital is. It's a probability. Don't be thinking that the little electron's doing this. Okay? That's what blows your mind right there. Oh my God, well, where is it? I don't know. It's just in there somewhere. Okay? Just be glad it's there. So, but you have a top lobe and you have a bottom lobe, and they're both part of the same. So don't be thinking that this is 6. It's not. It's 3. Okay? We're going to be using these, and we're going to be using the S-ort where you'll see we got some stuff to do with them. All right? Each is labeled according to its orientation along the X, Y, or Z axis. Okay? There is no rhyme or reason to the X, Y, and Z. It's just a designation. So don't think that, well, it obviously goes in the green one first, and then it goes in the blue one. They're all equivalent. But it would pick, so if you have 3 electrons, you'd pop 1 in each of the 3. Okay? Does that make sense? It's not, you can't just say that the X one is first and then the Y one. That's just convention that we do that. Okay, that we put them in that little order. Okay? Okay, so here is the ionic and the covalent bonds. Okay? Remember, ionic is transferring electrons. A classic example of an ionic compound is sodium chloride. Fluorine takes an electron, so now it has its octet. And so sodium gave off an electron, so what's left is the octet. Okay, so the octet, real important. Okay, but ionic is transfer, and covalent is sharing. And here is some pictures for you. I think they're on the slide. Okay, so when we share electrons, we can share them evenly or unevenly. We don't always share them evenly. Okay? And this is an example of even sharing, an HH single bond. Okay, there's 2 electrons in there. 1 came from each hydrogen. They're shaking hands. They are just happy campers. Okay, that's a nonpolar covalent bond. Here is a carbon bonded to a chlorine. Okay, they are sharing electrons, but the chlorine gets the electrons more than the carbon does because it has something. Would you know what that's called? What does it have over carbon?
Higher electronegativity.
Electronegativity. Very good. Okay? Electronegativity. So that's your polar bond. All right? Carbon also has less tendency to form a cation than a metal and an anion than other nonmetals. So you remember that to get an ionic bond, you would have a nonmetal and a metal. Okay? You'd have the 2. Okay, actually the metals are on the left. I should have done it that way since our table's there. So sodium chloride, that's a metal and a non-metal. Okay, we're going to talk about covalent bonds. So basically we're going to talk about non-metals. Okay, so did you draw little pictures like maybe of H2O and you put the little bond? Okay, that's what we're going to do next time. Okay? Okay, we'll talk some more about electronegativity. Okay, make sure I get your sheets. Just make me a little stack. If you have to ask me something, come ask me.
Are you done, Morgan? But I mean, it's not right now.